go slow. And today we will find out electric field intensity due to a charged conducting spherical shell. So let us suppose this is the spherical shell having radius r, and the net charge on this spherical shell is q. Suppose it is positively charged. So again we will be following the same steps. So the first step is a Gaussian surface. So Gaussian surface should be symmetric and closed. So in this case again we will be having spherical Gaussian surface, and suppose its radius is small r. So I can show the Gaussian surface over here. Suppose this is radius r and this is the Gaussian surface, and this is the point P where I have to find out electric field intensity. So second step will be flux. By definition, so phi will be equal to integral E ds cos theta. So as we did in the previous case, we will assume some element over here which will be directed radially outward. Electric field will also be in the same direction, so theta will be 0, and as we did in the previous case, this flux will become E into 4 pi r square. So this part is same as we did in the previous application. Next step will be to find out the flux using Gauss theorem. So from here I will split this application in 3 parts, because the point where we want to find out electric field intensity, that point might be outside, it might be on the surface, or it may be inside the spherical shell. So let us assume the first case. First case is the point is lying outside the shell. So like I have shown in the diagram, the point P is lying outside the spherical shell. So in this case, the radius of Gaussian surface will be greater than radius of the given spherical shell. Okay. Now let us follow the third step. So third step will be, we have to find out the flux by using Gauss law. So it states that flux passing through a surface is 1 upon epsilon naught times net charge. So this is the Gaussian surface, and inside the Gaussian surface the spherical shell is lying, which is having some charge, and that charge is q. So this q charge is inside the Gaussian surface, so the flux will become q upon epsilon naught. In place of q net I have placed q because it is the charge enclosed. This is equation number 2. And now the last step is to compare equation 1 and 2. So by 1 and 2 we can write that E into 4 pi r square is equals to q upon epsilon naught, and it gives us that electric field is 1 upon 4 pi epsilon naught q upon r square. Now this result is very important result because it gives us a very good consequence. The same electric field we obtained for a point charge, but now in this case the charge is not a point charge, but it is uniformly distributed on the spherical shell, but still we are getting the same expression. And now the point P, it is at a distance r from the center. So this result suggests us that for a point which is lying outside the shell, the whole charge is behaving such that it is a point charge, and that point charge is placed at the center. So it's like center of mass. The concept we discussed in class 11, that there is a point for a body where whole mass can be considered to be concentrated, which is called center of mass. So the same kind of thing we are getting here. Electric field for a shell, it is coming out to be the same like we had for point charge. So we can say that this whole charge, it behaves as if it is concentrated on the center. So that means this point can be called as center of charge in this case. Anyway, so this is the expression for electric field intensity for a point which is lying outside. Okay. Now, second case will be, suppose the point is lying on the surface of the shell only. So method will be same. We will be having Gaussian surface. We will be finding out the flux by the two methods and comparing the results. So we don't need to proceed the whole procedure. We will simply doing one thing, that for a point which is lying on the surface, this small r and capital R, they will become equal to each other. So directly I can place that small r is equal to capital R to get the electric field on the surface. So case second, electric field on the surface. So on the surface I can place small r to be capital R, and the result will be Es is equals to 1 upon 4 pi epsilon naught q upon capital R square. So this is electric field at the surface. Okay, now the third case will be, the point will be lying inside the spherical shell. So let us find out the electric field over there. So these two steps are same. Now inside the shell, suppose there is a point P which is inside, and let us assume a Gaussian surface over here. So now Gaussian surface will be this one. So let us apply Gauss law and find out the flux. So Gauss law states flux is 1 upon epsilon naught times net charge enclosed. So as you can see in this case, the whole charge is lying outside the Gaussian surface. See, this is the given spherical shell and this is the Gaussian surface which is passing through the point where we have to find out electric field. So in this case, this whole charge, it is lying outside the Gaussian surface. So that means the charge enclosed inside the surface will be 0, and hence the flux passing through Gaussian surface will also be 0. So this is equation number 2 now. So again the last step, this was the third step. Now fourth step will be using 1 and 2. So by 1 and 2, if we compare the results, we will get E into 4 pi r square is equals to 0, which gives us electric field to be 0. So that means electric field inside the spherical shell will be 0 only. So now we are having the electric field in all the three cases. Inside the shell electric field will be 0, and at the surface it will be 1 upon 4 pi epsilon naught q upon capital R square, and outside it will be E equals to 1 upon 4 pi epsilon naught q upon R square. So for graphical representation, okay, let's see. So on x-axis we are having distance. So as you can see, this is the center of the shell, and there will be a point. So at this point small r will be equal to capital R. So that means beyond this point we are outside the shell, and this side of the point we are inside the shell. So let us show the graphical representation of electric field. Electric field will be taken along y-axis. So at the center is inside the shell, and we know inside the shell electric field is 0. So that means at this point electric field will be 0 only, and up to this point where r is equal to capital R, that means along these points electric field will remain 0, because we have shown inside the shell field is 0. So graph will be something like this. So as you reach at this point r equal to capital R, means you are at the surface of the shell, and at the surface electric field, as we just calculated, it was q upon capital R square. And then if I move beyond this point, that means I am going outside the shell. So outside the shell, field is inversely proportional to square of distance. So variation will be shown something like this. So this is electric field outside the shell. So this is a graphical representation of electric field. Don't forget to write down this point, that for a point at the surface or outside, the whole charge, it behaves as if it is concentrated on the center only. That means it starts to behave like a point charge, and we can also call the center as center of charge. Thank you.